Okay, good afternoon, everybody. I'm Stephen Hegedus, I'm Director of the Kaput Centre. I welcome you all here today. This is the second half of the Symposium, led by Professor Martin Simon from NYU. It's a pleasure to have Marty here today with us, and we spent the morning at the Kaput Centre, and now we're here in a beautiful, newly renovated library here on the Dartmouth campus. So for those of you who are visitors, welcome. Those of you tuned in online, welcome. Thank you very much. Apparently the Twitch service is no longer working. I've just been informed by Rob, which means you can't Twitch us. Is that the right verb? So if you wish to ask a question, you can go to the blog site. Okay. The way that Dr. Simon wants to run today is he will take very short clarificatory questions during his talk, and then leave your longer questions for the end, which will be the last 30 minutes. Okay? Dr. Martin Simon is a professor of mathematics education at New York University. His research focuses on understanding mathematics learning, particularly the process by which students develop mathematical concepts through their activity in the context of a series of mathematical tasks. His current NSF-funded project combines basic research in this area with research on a measurement-based approach to fostering strong fraction and ratio concepts. His earlier research focused on the development of teachers as they learn to teach mathematics with a conceptual focus. He has developed new research methodologies and published articles on issues of quality in qualitative mathematics education research and the use of multiple theories of learning. Marty is a leader in the field of mathematics education. His work has been numerous, diverse, and very influential. It is a great pleasure and honor to have him here today, and I welcome him to the floor.
Thank you, Stephen. Definitely been enjoying my day here. Nice to see some of you who weren't here this morning. Anybody who is here on Friday afternoon, late afternoon, you're either very dedicated or you need to get a life. So as I said this morning, it's a privilege to be invited to the Kaput Center because Jim was a good friend and colleague, and it's my first time here, so I'm really pleased to be here. Stephen covered that. So let me see who's here. Are there school teachers here? Okay. Math education faculty, other education faculty, mathematicians. You can't raise your hand. Anybody whose category I didn't mention?
No lifers?
Engineers? People have a life. They're not here. Okay, so for those of you who are, particularly the teachers, if some of the nitty-gritty research parts are less in your interest area, then please focus the discussion part of the talk more towards the instructional aspects that I will talk about. So the basic problem is how to foster conceptual learning. And we've acknowledged for a long time that just showing and telling has weak results when the issue is conceptual understanding. Showing and telling is actually a very effective way of doing a lot of things, but not developing deep understanding of concepts. For example, if I want you to know my phone number, telling you would be a very good way to do it. Anything else would be very inefficient. So, if showing and telling doesn't work very well, and then the other thing we observe is that math is not in the representations or problem solutions that we encounter. In other words, that students can't see the math in the representation. Then what we wind up is a situation that students cannot perceive a new concept. They cannot take it in from the outside. So what's often done is what I term a problem-solving approach, which is we give students problems that require the new mathematics. And of course, there's an inherent problem in that, inherent difficulty in that, which is that if you don't know the mathematics, you don't have a very good chance of producing the mathematics that you're there to learn. What typically happens in a lot of situations is that a few of the students in the class can solve the problem, or solve the problem the way desired by the teacher, and that's either because they're advanced, they were sort of right at the about to break through, or they already knew the mathematics. And then during the class discussion, they present their solutions, and essentially they tell the other students how to solve the problem, which takes us back for most of the students to a situation that's not that different than when the teacher told them how to solve the problem. So, how do we help students build concepts? I made people answer that question this morning. The results were like the results I usually get, was it got pretty quiet. So, our work is designed to try to figure out a way to understand mathematics learning at a level that's useful for teaching and instructional design. I say pedagogy because teachers don't have full responsibility for teaching. It's a co-creation between teacher, curriculum designer, materials designer, and so on. Again, if there's something I say that's not clear, if you please raise your hand and I'll try to clarify. And the other goal is to develop instructional design principles based on the understanding of learning. Okay, so ultimately we want to figure out how to teach based on some way of thinking about learning. In this talk, I'll be emphasizing the former, which is the inquiry into students' learning. In fact, they co-emerge. This is as creative as I get on a slide, so please appreciate this. I know, pow is what you're saying, right? So basically, in doing the kind of teaching experiment work we do, we have to have some kind of instructional approach, because if we don't foster the learning, we don't get to study learning, right? If the student doesn't learn, there's no learning to study. But of course, if we knew everything we wanted to about fostering the learning, we wouldn't be studying it at all. So it's a cyclical kind of thing where we start out with an initial hypothesis about how to foster the learning. We have some degree of learning, which we learn more through the analysis of that learning that feeds back in, and it improves our instructional approach, and it keeps working in this way. So, how to foster deep understandings of what turn out to be difficult mathematical ideas for students is a tough problem. And there's a question beneath it, is to what extent can we analyze and explain learning? I had a discussion with somebody the other day, a math educator who was doing research, and I said, but you're just focusing on the behaviors, you're not focusing on the student's understanding. And she said to me, well, how can you pay attention to the understandings? You can't see understandings. I said, yeah, that's the kind of work we do, is inferring understandings from students' behaviors, students' verbalizations, and so on. So, understanding learning goes a step further, right? It's not only about understanding where they are at any point in time in terms of their understanding, it's trying to understand how that understanding is evolving in real time. So it's a difficult problem, and the question is, to what extent can we do that? Now, either I'm crazy or I believe that we can make some progress on that. Or both. So what I want to emphasize here, and I emphasized it this morning, is a lot of the work that's been done and called research on learning of mathematics actually is a research on identifying the steps, the conceptual steps that students pass through as they develop particular understandings. So one of the major leaders in the field has been Les Steffi, and he characterizes the various schemes, whether it's an early number or fraction. He characterizes the schemes that students develop in a somewhat hierarchical fashion. And our work differs in the sense that we're trying to look in detail at how students develop from one scheme to the next. Hershkovitz and al. Said, in spite of the animated theoretical debate that has taken place on the nature of abstraction, little experimental research is available. We surmise that the lack of experimental evidence is due to the difficulty of observing the process of abstraction, as opposed to the products for which there is more evidence. Okay? Another way of saying the same thing.